The next topic I'm going to talk about is so the next topic I'm going to talk about is beam theory. But in this topic, I'm going to be a little more explicative of how we develop the beam theories. So what you typically learn in mechanics of materials is a 2D case. Just a simple cantilever beam when you look at the side, or a simple supported beam. But what I'm going to teach you is a 3-dimensional derivation for this. So this can apply to more than just one application. And you can basically use a series. The advantage of this is using a series of system equations that help you identify the solution to a simple beam, to a beam problem that has multiple dimensions of loading or kinematics that you have to consider. So for this beam theory, it's actually advanced beam theory. And we're going to be using, and the correct terminology for beam theory is Euler Beam Theory. So, like all engineering approximations, it starts off with assumptions. So we make the following assumptions in order to navigate through beam theory. And these assumptions must be met before you use or utilize this method. Otherwise, you may stray and achieve solutions that don't necessarily reflect the physical, behavior of the system. So, first assumption is a beam's length is significantly greater than any dimension in its cross section. Okay. So what we essentially mean by that is, okay, let me go ahead and draw a generalized beam real quick. If we have simple cantilever beam here, has some arbitrary cross section here, consistent length here. We'll say through the thickness length is A, and the side width of the beam we'll consider B. What we're essentially saying here is the length of the beam is so much greater than A or B here that A divided by the length, or the width divided by the length, is an extremely small number, and this is the definition I use. So this varies from person to person. What I like to say is these numbers have to be smaller than 1/10. That's what I consider smaller cross dimensions. So now this is opinionative for many others. This is just the notation I use. Okay, so there's that assumption. The next assumption we have to assume is for tapered beams, they can be analyzed if the taper angle is not steep. So in other words, the taper angle, which is given in radians, is significantly less than, and again, for me, it'll be 1/10. So taper beams can apply if this is met. Next thing, so this assumption is for a notation's sake, to keep beam analysis consistent in literature. We always make the longitudinal the x-axis. Keep things consistent with others who analyze beams. Next assumption, a force acting on a small area can be considered a point load. So that one's pretty self-explanatory. Now, in lieu of that, we also can consider distributed forces. I'll get over, I mean, you guys have probably seen distributed forces before. For example, weight of a system or weight of a beam is considered a distributed force. Surface traction, like surface pressure, couples, or maybe you've seen examples of distributed couples. These are also forces we need to consider in this theory. So that's the general. The main point here is that a point load can be considered when a force is acting on a small area, but the others we need to take a look at as well. So the next assumption here is the plane of the cross section of a beam must always, I mean, not must, but is always normal to the longitudinal, or sorry, the center longitudinal axis of a beam. So what I essentially mean by that is, take for example, if a beam like this were to deflect upwards, right? If we look at a mid-plane axis that goes through the beam, I should draw this bigger actually. What I mean by this is that, let's take for example a beam here, a cantilever beam. If the beam were to deflect as such, and we would draw an axis about the camber of a beam, this axis right here would always be perpendicular to the cross-sectional face along the length of the beam. So that's essentially what this means, and that's an important assumption, so we don't have regular compatibility issues when analyzing Euler beams. So the next assumption is that the origin of a cross section is located at the centroid of at the centroid essentially. So this is plainly obvious. If you guys remember your centroidal equation, so for example, if we were to look at the cross section of a beam, so in the cross section of a beam, I'm going to draw it arbitrarily, something like this. We have a z-axis here. Sorry, this will be the y-axis, z-axis here. So this is my general notation too. So we consider the x-axis the longitudinal of the beam. I like to make the y-axis the transverse of the beam, and the z-axis what you would consider if you were to look at this thing at the side. This would, the z-axis would go out of plane like this. So to find the centroid of an arbitrary face, if you guys remember, it would be, oh, not x, we're using z this time. Z, the integral of the general shape, whatever function you establish the shape of that beam to be, dx over, again, that general shape, the integral of that general shape with respect to x. This is essentially equivalent to the sum of the center of each, the x directional center of each proponent. So you can split this up into multiple parts. So yeah, the directional center of each x direction times each component area divided by the sum of each component area. And there I go, making it z and x again. Okay, so it's just to keep this consistent. We're going to write it as x. You can just replace things as z to match this cross-section here. Then y again here would be as follows. Okay, so this is how you would find the center. So yeah, we would just assume that the longitudinal axis, the x-axis, passes through that centroid, and any dimensional value that we entitle onto this beam, for example, if we want to go establish a y coordinate, it has to be with respect to the centroid. So that's all that statement says. So distributed loads, I need to just mention right now, distributed loads or distributed couplings, for example, looks something like this. If you have a cantilever and a circular beam or bar, you'd probably take your hand and twist it. You would have a distributed moment like this about the longitudinal axis. Okay, so there's that. The last assumption we need to make is that the cross section, when the cross section moves, the cross section moves rigidly. So what this essentially says is that there is no deformation in the cross section. Okay, so that simplifies things when we go further into this analysis. Okay, so now we're going to go ahead and move into the notation for beams. So the general notation from beam theory . So the general notation from beam theory, let me just go ahead and draw another arbitrary beam again. Okay. So the general notation for beam theory, or for beams in general, when we apply, for example, a moment onto the beam, and I'm looking at the beam at the side, when we apply a moment to the beam, essentially you would use the right hand rule. So you would get your right hand, and since the z-axis is coming out of the page, and you would look at the free end, or essentially the end where you establish your moment, where you establish your moment load, and you essentially, and your thumb would point in the direction of the z-axis. If you're going about, if your thumb is pointing in the direction of the z-axis and the rest of your hand is coupling in the same direction the moment is going, then essentially you have a positive moment here. Some people simplify this by just saying that this makes a smiley face here. So for something like shear forces, if it goes in the positive direction, your applied shear force goes in the positive y or z direction, then it's a positive shear force. And obviously there's going to be a reaction right here. So that's what we term, that's our beam notation for positive shear moments and shear stress forces. So the next thing that I need to establish is our notation for what these how we essentially relate these moments to equivalent stresses applied onto the system here. So if I just take this cross section and here's y, here is z. Oh wow, that looks kind of weird. Okay, so if I take this cross section here and I essentially pick an arbitrary point here in the positive y and z direction, this point has an area, particle area dA, and if I apply, and this area right here is has the following stress elements in the positive directions: tau x, y positive, tau x in the x face, and in the z direction, tau x, z positive. And now we obviously have sigma x, and that's in the positive x direction here. So if we establish a system like this, a coordinate system like this, hold on, I need to fix the so if we establish a coordinate system like this, and we assume that a singular point here undergoes the following stress state, we can assume the following for the moments and normal loads applied to a beam. So the moment of a beam would be negative tau xy times z. So z being the moment arm here, tau xy, it's going about the so this is a moment about x. So it's going about the x-axis with my thumb pointing in the negative x direction. So that's why there's a negative in front here, plus tau xz times y dA. Okay, so that's how we establish the moment about the x-axis for this theorem. X1 is moment about y, which is z times sigma x, and sigma x can be, so moment about y, the only proponent that we need to worry about is the normal stress sigma x here. Sigma x obviously is a function of x, y, or z coordinates. I'll show you how to derive this later. Okay. Moment about z, same thing for moment about y. Moment arm y times sigma x dA. Okay, and obviously our normal load, sigma x times dA. And our shear loads are kind of self-explanatory too. Shear load in the y direction, 0y, tau x y dA, and then v, or shear in the z direction, tau x z dA. Okay, so we're just going to go ahead and establish this as our equivalence of finding internal moments due to stresses. I mean, the internal loads due to the stresses acting on the beam. So now that we've established this in beam notation, we're going to go ahead and establish the differential equations of equilibrium for a beam. So essentially, what are the governing equations that dictate how a beam behaves? So let's go ahead. Differential equations of equilibrium for beams. Okay, so starting out with the first equation of equilibrium here, it's simple mechanics and materials method. So let's go ahead and sum forces in the x direction. So let's assume we take a section of a beam, some delta x of a beam. We have one side applied with a normal stress, a normal load, another side applied with a normal load plus an additional increment of load. That additional increment is the only way we can establish a disturbance in the equilibrium of the system. So that's why we always add this additional term here. And we will have some distributed normal loads happening with on the beam. We'll just call this a fancy P. Px is a function of x because this doesn't have to be uniform. It can be distributed in a given quadratic or some polynomial form equation. Essentially, what we do here is if we sum forces in the x direction, and since this is a static problem, it has to be 0. Sum forces in the x direction, we get P plus P dx delta x, right? Plus the distributed normal load here, Px, multiplied by delta x, minus load right here, P, going the opposite x direction. So we'll just consider this positive x. This has to equal 0. Essentially, what you get here is the following equilibrium equation. Those p's will cancel out. This delta x terms cancel out afterwards. Partial derivative of the normal load here with respect to the x-axis is equal to negative of the distributed normal loads here, px. Okay, so this is a very effective equation. Essentially, if you have a distributed normal load, you can relate it simply to a singular point concentration normal load by just carrying out this integral here. And if it looks fairly obvious, this integral here would essentially be delta x if you move the partial x over here. So this is our first equation. So our second system equation. So you can do the same thing for your shear stresses. I'm not going to draw out the diagram, but essentially if you sum moments about the y, you sum forces in the y or z directions, right? So if you sum forces in the y direction, for example, you yield the following. Okay, so essentially this can be simplified to partial derivative of shear loads in the y direction with respect to x is equal to negative distributed load in the y direction as a function of x. So that's equation 2. And in the z direction, it's essentially the same method. Negative x. Okay. So that would be equation 3. So those are the first 3 equilibrium equations. Now we have to establish the equilibrium equations for moments. So equilibrium equation 4. So equilibrium equation 4 would be as follows. For 4, we would just, all right, so we have, again, take a section of a beam. Let's say there is some distributed loading in the y direction. We apply a shear here, shear plus a little bit extra. Okay. And then some moments about the z-axis. We're obviously assuming we're assuming everything's in positive notation. For completeness sake here, let me just give you the coordinates or a coordinate orientation, just like that. Okay, so let's go ahead and some moments about the right-hand side of this element here. So we do that, we essentially get mz plus dmz, or partial derivative of mz with respect to x, times delta x, that whole thing minus moment about z plus shear force in the y direction times delta x minus distributed load in the y direction multiplied by delta x divided by 2 times delta x equal 0. Okay, so essentially what this, if you simplify this term and then you take the limit as delta x goes to 0, because we want to evaluate the behavior at this theme with the smallest equivalent conjugate element as possible. So we take this whole thing and simplify it here. We would yield the following. Partial moment about the z-axis with respect to x is equal to your shear load in the y direction, or negative shear load to the y direction. So you guys have probably seen this equation before without the subscripts here. The moment, partial of the moment with respect to x is equal to negative of the shear forces. So this is consistent with what you've probably seen in mechanics of materials. Do the same thing for about the x-axis and about the z-axis, and you will yield the following. Partial moment of the y-axis with respect to x is equal to positive shear in the z direction. So that's equation 5. And finally, equation 6 right here would be partial of the moment about x distributed moment couple minus the distributed moment couple about the x direction, in the x direction of the beam. Again, this doesn't have to be uniform. And there we go. We have 6 equations of equilibrium, or 6 essential differential equations that describe the loading state of a beam. So these are really useful, and you'll see in later parts of this derivation how they can come in handy. So the next thing we need to talk about is the kinematics of a beam. Kinematics of beams here. So kinematics of a beam is we're going to have to make a couple of, this here is also where we're going to have to make a couple more assumptions. So we progressively make more and more assumptions as we go along this derivation. Okay. So here we just have a simple cantilever beam. This direction here. Let's assume it bends like this. This direction being y. And let's look at this in top-down direction. If the beam were to bend like this, in a top-down direction, the z-axis would be here. So the y would go, would be coming towards us. Here the z-axis is coming towards us, right? We would assume that it is bending in the positive y direction here. Okay. Okay. So let's assume a beam kinematically deforms as such, about the positive z and positive y-axis. We take a point, some point right here in the positive z or y-axis. So here in the positive z, here in the positive y-axis right here. We take a point and we establish the following kinematic relationships here. So the displacement in the x direction, so the displacement in the x direction, delta x, will equate that to the letter u. So lowercase u is equivalent to first the displacement at the middle of the beam, or the centroid of the beam. So we call this a midplane strain. The midplane displacement u, which can be a function of x plus z times the rotation about y. Okay, so let me explain what this essentially is, right? This essentially describes the when you rotate the beam. So this is rotation about y. So we have to look at this system right here. Rotation about y. When you see the beam deflect this way, essentially, if you analyze a point right here from the original undeformed configuration to the deformed configuration, you can see that it sort of moves backwards. So that's sort of the logic behind this equation right here. But many of you realize that this has a positive here. Well, so it moves back in the negative direction. So we normally would put negative z times delta y. But here's the thing, right? We're analyzing this point right here. So we're analyzing this point right here, some z direction. But the beam is bending. If you use the right-hand rule, your thumb will be pointed away from the screen, so away in the opposite direction of the y-axis. So this bending right here would be considered negative. It moving the displacement back would be a negative, so two negatives basically make a positive here. And then that's not true for the next case where y, rotation about z-axis, right? So just by looking at the kinematics here, if I take the cross section here, I look at the camber of a beam. If I look at this camber and I basically look at this angle here, this angle delta y here, and transpose this so that we can make the equivalent triangle here. Okay. This equivalent triangle here, let me go ahead and explode this here. That equivalent triangle, we something like, here's delta y, here is deflection in the y direction. So deflection in the y direction, we're going to equate as v. And then with respect to whatever proponent of x direction, whatever little part in the x direction we take off of this beam. So now that we have that, we can essentially say, and using small angle theorem, using a small angle assumption, that sigma, sorry, this is in the z direction. So I'm going to go ahead and fix that. This is rotation about z. Rotation about z would be sigma z, or theta z would be equivalent to partial of deflection in the y direction, which we call v, with respect to x. You do the same thing with the rotation about the y. So dw, which is deflection in the z direction, partial with respect to x. Okay, so essentially here we have an equation for the kinematic normal displacement of the beam. We can insert these made rotation assumptions here to achieve the following using small angle theorem. The displacement as a function of x, y, or z positions is a equation that is the midplane displacement, okay, my bad, I forgot to put a negative here. The midplane displacement minus z dw dx, okay, minus y displacement in the y direction with respect to x, okay? So that's our equivalent of the elongation of the beam normally. For the displacements of the beam in the y and z direction or transverse directions, we just assume the following: that it is simply the midplane displacement as a in the y direction as a function of x, and w is the midplane displacement as a function of x. Okay, so there we have that. The next thing we need to establish is our kinematic relations to strain. So if everybody knows longitudinal strain is basically, for a beam, a longitudinal strain would be the elongation delta L divided by L, or elongation x direction, whatever respective x length that you choose. So that's how we establish the strain. We equate that, and this equation, it's established using an infinitesimal assumption for Lagrange, green Lagrange strains. I won't go into detail about that, but essentially the equivalent for normal strains in the x direction would be the displacement in the x direction divided partial with whatever position x direction you choose. So with this relation, we essentially take this equation right here with respect to x, and we get the following. Strain in the x direction is du dx, which is equal to midplane strain minus times second order partial of the displacement in the z direction with respect to x minus second order partial y direction with respect to x, okay? And you yield this equation right here, which will be important for later. Hold on, let me box that a little better. So you yield this following equation right here. And you'll notice this term here and this term here are your curvatures. So if everybody remembers the equation for a curvature, let's just assume curvature in the going in the z direction, equation would be something similar to this right here. But we assume that this proponent and anything past that is really small when you square it, so it becomes 0. So essentially, the curvature is just the numerator portion. So this is curvature with respect to z, and this is curvature with respect to y. So we essentially have an equation that relates strain to the curvature and mid-plane displacements of beam, which is very powerful. Now, we relate that to the constitutive equation for a beam. The general constitutive equations. So, constitutive equations, right? If everybody remembers, from Hooke's law, we're assuming an isotropic beam, by the way. It's probably another big assumption that we need to make. Assuming the material of the beam is an isotropic material, is the following. So this is now the compliance matrix. And I'm only concerned about the top row here. Poisson ratio by okay, so here's the thing. I'm going to assume the normal stresses in the y and z direction are so small that we can neglect them. So I'm going to call them 0. So the only thing we're worried about here is sigma x. Okay, so with that assumption established, our constitutive equations is as follows. Strain in the x direction is equal to 1 over the Young's modulus times sigma x. Okay. Now, that essentially means the normal stress in the x direction is equivalent to Young's modulus times strain in the x direction. This is equivalent to, so we already have an equation for strain in the x direction. This equation that we've established up here gets substituted here, so x, okay, minus e times z d squared w dx squared minus Young's modulus times y squared v dx squared. Okay, so this right here is now our constitutive. This right here is basically our governing equation for a beam that relates the constitutive and differential equations into one singular whole equation here. So we're going to take advantage of this in a bit. But now we have to go ahead and utilize the moment and normal load derivations that we established earlier for a stress state in the beam, and try to apply that here so we can complete the equation for application, we'll say. Okay, so how we do that is the first thing we're going to do is the very first thing we're going to do is take the normal load. It's a function of x, normal stress, and essentially we apply our normal stress equation here into this, so we have the following, or we yield the following. du0 dx dA here, okay? Oh, drew this wrong. Negative y differential with respect to A, our differential with respect to cross area, minus Young's modulus times d squared w dx squared, okay? This one right here, oops, I actually made a mistake. This actually doesn't come in yet. Okay, so first part would be Young's modulus times the normal strain with, normal displacement with respect to x times the integral of the area minus what would pretty much be the integral, see, with respect to the area. Finish it off here. D squared v dx squared I respect to area. Okay, so you yield the following equations. Now, if you basically carry out the integral here, this goes to 0 and this goes to 0, so you're only left with here. This integral of area with respect to constant is simply just area. So you'll yield the following equation. Your equation for the normal load would be as follows. The Young's modulus times the displacement in the x direction with respect to x multiplied by the area. Now, if you guys remembered, this is sort of equivalent to your Flee equation. If we assume that this right here be delta L, dx is equivalent to L, and px is equivalent to F. This equation right here, I'm going to go ahead and box it really quick because it's one of our essential equations we need. Equation 7. This equation right here can be written as delta L equals FL over EA. So that again is the elongation in the x direction that you probably learned in your mechanics and materials class. So pretty neat that we've been able to achieve this through these system of derivations. So the next thing that we need to do is, now that we've taken care of the normal load, we have to take care of the moments. So moment velocity. So I'm going to be less detailed or explicative about this derivation here. Okay, so that's how we establish the moment about the z-axis with the internal stress in the x direction. This becomes Young's modulus times E this to negative y dA. This, if you do the derivation, goes to 0, plus E d squared w dz squared, okay, y z dA plus E squared v, that's a v, sorry, dz squared, y squared dA. Okay, so this section goes to 0, so you only have this section right here. Now, if this and this look familiar to you, this is your definition of inertia. So this becomes I, y. This becomes I, y, z. So those are your moment, or inertia deformations. So if, for example, if you did the calculation, if you did the integral for this for a rectangular cross section, you will get your traditional b times, or b times h cubed over 12. So you'll yield the same equation. So yeah, it's very interesting. We gather the second moment of inertia terms through this derivation. So we've essentially developed the moment about the z-axis equations that relate the curvatures with the material property of the beam to the second moment of inertia, second moment of area for the beam. So with that interesting development, we also do the same thing for the moment about the y-axis here. So my is, let's see if my is equal to Young's modulus, and I'm going to go ahead and just include the moment of inertia terms already. Z, the second moment of area, actually, e squared w dx squared plus Young's modulus times z squared v dx squared. Okay, so there's that. Essentially, you can boil these guys down into a matrix proponent here. So we take mz, and we take moment about y. That is equivalent to, just gonna move e out here, I z z negative I y z. This is reflective and diagonal. This matrix right here is diagonal symmetric. And then I y here. Okay. Multiplied by the curvatures, d squared v dx squared d partial derivative, second order partial derivative in the z deflection with respect to x here. Okay, so now that we've established this matrix set of equations right here by equating these two moments, we can essentially find the curvatures in order to produce okay. We can essentially find the curvatures by reorganizing this matrix equations and taking the inverse of this matrix right here to the other side. So by doing that, yields the following. The curvatures, d squared v dx squared d squared w dx squared is equal to 1 over the Young's modulus times a term we'll call delta here times Iyy Iyz Iyz and Izz. Okay, multiplied by your moments. Okay, so that relationship established, and the delta term I put here is Iyy, second moment inertia about y, second moment inertia about z, subtracted by square of the cross inertias. So with this term here, we're essentially able to find the curvatures with respect to the given inertia, the moments, and the material properties, all of which we should be able to solve when beginning the problem. So this is advantageous for us because these curvatures right here are seen in our, I'll just try to find them, they're seen in our normal stress equations here. So we're just going to go ahead and plug them into here by carrying out the matrix multiplication. So everybody remembers basic matrix multiplication. On the left side, go row, then down column. So IYY times MZ plus IYZ times MY. Matrix multiplication here, we will just establish that d squared V d. So partial derivative of displacement in the y direction with respect to x is equal to I, y, y, m, z plus I, y, z, y for, okay. Okay, so this first equation right here is equation 8. One of the essential equations we need. Equation 9 would be this. Okay, so second important equation here. Now, what you might realize from these equations, right, is, for example, if we have a symmetric cross-section. So these examples, I've been using a cross-section that's sort of oblong shape and arbitrary, but if we use a symmetric cross-section, say a rectangle, for example, when we use a symmetric cross-section, IYZ becomes 0. So the cross-second moment of inertia becomes 0. Cross-section. With that, these equations will boil down to the following, which is something you've basically seen in your introduction to mechanics of material class. Sorry, this is supposed to be an X. Without the subscripts, you should be familiar with this derivation right here. And then this IZZ. This is one of the governing equations. Let me draw this so that this Z looks more like a subscript, but this is the governing equation for second order deflection with respect to X being a function of the moment, Young's modulus, and inertia. So if you drop the scripts here or subscripts here, you'll basically get something familiar to what you've seen in mechanics of materials. And same thing if you take out and make the cross-section second moment inertia equal to 0 here, you get the equivalent for the displacement in the Z direction. So another overlapping consistency of equations that we've seen in basic mechanics of materials. So if I take advantage of this, so with symmetric cross-sections, we're essentially able to boil down the following relationships. And these relationships, I'm going to emphasize again, they're only for symmetric cross-sections. D squared V dx squared. So second derivative of displacement in the y direction is equal to moment about Z divided by Young's modulus times inertia about y here. Okay. So we've established this earlier. Oh, sorry, not about YY. I meant to say about Z. Okay. And we know the following relationships because we derived this earlier, that the moment about Z respect to X is equal to, from our differential equations we established earlier. We apply this into here, we yield the following. So this is a cubed. So third order differential. Actually, let me go ahead and make this a little better. Third order differential is equivalent to times okay. This in turn becomes times I z z cubed third order differential right. So again, drop the subscripts and you have something familiar and consistent with mechanics of materials. You can also yield the following here. IZZ. Oops, I meant to say IYY. D cubed V, or displacement in the Z direction with respect to X, third order. V. Okay, so go ahead and box this equation right here and box this equation right here. Go ahead and make this box a little better. And I'm going to go ahead and call these equation 10 star, the star implying that this is only applicable for symmetric cross sections, all right? So third order, so if everybody remembers, the differential equation, when you plug differential of shear force in the y direction with respect to x, you get the distributed normal. You get the distributed normal forces in the y direction. So essentially apply that there from our original equations, and we yield the following. Let's see, d. It's a power of 4 now. It's equal to negative distribution with respect to y. It's a function of x. Young's modulus. This part really is not that concerning. Okay, my bad. I meant to say a little mistake here. And yeah, you yield the following, which is again consistent with what we've seen with the introduction to mechanical material class, just by removing the subscripts. If you can't tell, this right here, and I'll get into this later when we do an example in a bit, this is how you would find the deflection of a beam. And et cetera, for the normal distributed loads in the Z direction. Okay, so we will call that 11 star. Okay. So That's really just a side note. So now we're going to go ahead and we're going to apply our equations of curvature into our equation for normal stress. We're going to get what's essentially stresses in beam, the singular equation used for stresses in beams. So stresses in beams. So we assume the normal stress is the only significant and ubiquitous one for this derivation. Sigma x is equal to P over A plus Z, moment about Z, plus second moment inertia about Z, moment about Y, all divided by that delta term I specified earlier, times Z, minus second moment of inertia about Y, Z plus I, Y, Z times my for that delta term I specified earlier times y. Okay, so this whole entire thing right here is essentially your normal stress in the beam, which is amazing because this encompasses pretty much everything you guys are familiar with. So here, P over A, that's your normal stress. You learned that from basics, stress and strain theory. But right here, right? So if this was a symmetric cross-section, and this is equation 12, by the way, if this was a symmetric cross-section, then IYZ would go to 0. And let's assume that there is no normal load. So if symmetric plus no normal loads, you get your advanced equation that you probably already learned in your mechanics of materials class about asymmetric bending. My, this would be YY, yeah, this would be YY, right? Yes, times Z minus MZ I Z Z Y. So it looks familiar, stems from this huge equation right here. So essentially, the only thing you need to remember is this one singular equation, and you can solve for all the normal stresses in the beam. And this is really helpful because many people sort of think of these two separate as two separate entities that conjoin and occur when you put together a stress matrix, but no, you can simply write it as one uniform equation right here. So, oh, by the way, the P over A, just for numerical completion, we've established somewhere in the stress equation right here. See if I can go further, if I have a further, that if I move the A here, E times du, or the displacement in the midplane with respect to x, the differential of the displacement in the midplane with respect to x times the Young's modulus equals the normal load divided by A, which we substitute that into here, and we substitute that into the stress equation. So for completeness and numerical sakes, that's why that's there. Okay, so yeah, essentially we have now the stresses in the beam, which is a very powerful statement in itself. So now that we have all these derivations and we have all these equations we can use, how do you use this for your specific application? Now, we go ahead and insert. So steps to use this derivation. It's actually really simple. The first thing you would do is you would just find mz or my or your shear moment or your shear forces using the differential equations we established, which are equations 1 through 6. Afterwards, so I'm going to say this is not just 2, but 2a. You can go in two different paths here depending on you. You can find the stresses using equation 12, or 2b, you can use equations 7 through 11, and then we put a star there because 11 considered symmetric, 10 and 11 considered symmetric conditions to get deflections. So this is a really powerful statement, this is a really powerful method. Essentially, we can get both the stress quantities, or define the stress state of a beam, and also identify how it deflects simply by using the established equations that we developed during this derivation. So, and really it doesn't require a whole logical progression of steps in order to get the final value. You simply just need to know what you're looking for. So before we get into example, the next thing I need to mention about this is inertia. So over here, if I can find it, so over here, we established that inertia could be separated, or could be split into several components into this matrix equation. So inertia has its own matrix. So this right here, this inertia state matrix right here, is equivalent to stress state matrix. So inertia actually has its own principal axis, and it has its own Morse circle. So about inertia, it has its own Morse circle. So essentially, it has, in the vertical direction, let's just say some cross moment inertia. And then we have our regular inertia about an axis, say. Okay, so again, we developed this circle, and let's see if we can get through this through the center. If this is a center here, I just need to draw a consistent point in between them. Okay, there we go. Okay, so we have a point right here. Let's just establish this point as our positive. We can establish this point right here as so like that. Inertia itself has its own Morse circle. So you can basically determine the orientation, this right here, the orientation of your maximum moment of inertia just by simply using the Morse circle equations we used earlier. So to establish this, and right here would be the maximum inertia, and right here would be the min. And why is this advantageous? It's because if you design a cross-section, particularly a cross-section that is not symmetric, and you want to take advantage of this of the state of inertia so that you have no cross-sectional area or cross-sectional moment area to worry about, essentially this this will allow you to identify whatever orientation angle you need, so you can design your parts in such a way where even your maximum or your neutral axis corresponds to the orientation of your moment inertia. There are some applications where this is advantageous. I won't really bring them up, but it's an interesting phenomenon to really evaluate here, or really gather. So same thing with Morse circle for stresses. This is your average inertia. Y squared over 2. And this right here is the radius of the inertias. Okay? Right. So now you probably want to know what orientation you need to angle, or what orientation from the primary inertia axis is in the x and y direction do you need to angle your part in order to achieve those maximum moments of inertia without having a cross-sectional or cross area second moment of inertia. That would simply be by just taking the tangent, or that would simply be finding the inverse tangent. So with this relation, so remember, phi and theta are related to each other by a factor of 2. Simple tangential equations for 2. Okay, so that's essentially how you find the orientation to take advantage of this relationship here. Okay, probably another thing to bring up is parallel axis theorem. Just a quick reminder of what parallel axis theorem is, because you're probably going to have to use it to find some inertias. But honestly, nowadays, everybody just uses an online engineering tool to do this for you. So if you want to do this by hand, and I'm just going to show the parallel axis theorem for the x direction. By the way, this is bar as in if you take something that has this sort of cross section, you split it into 2 parts, 1 and 2 here, you are going to look at in the x direction, where's the centroid of shape 1 and shape 2 here, and obviously you basically sum the inertias in the x about the x-axis for all different sections you split your cross section into. And then this is the only other one I want to mention, because that would probably, so that specific portion, cross-sectional moment inertia, plus the distance from the centroid of the whole component to the centroid of that part in the x and in the y times the area. So there is that. Okay, just make this look a little more cleaner. So there is that. I think the only other major thing we need to talk about before we get into examples is where the maximum stress of a beam would be. So first thing we need to discuss is the neutral axis, because you need to understand how you can find the orientation of the neutral axis before you can find your maximum stress. So everybody knows essentially what the neutral axis is. So if I have an arbitrary cross section like this again, I have z direction here and I have my y direction here. Some angle will yield me an axis, the neutral axis, where on this axis stress is equal to 0, because remember, bending can only happen if one side experiences a positive tensile stress, the other side experiences negative compressive stress, or by notation negative, and by notations tension is positive. So let's go ahead and put an additional set of text here. The neutral axis passes through the centroid of a cross section. Okay, so fairly obvious there. Next thing, the normal stresses are 0 at the neutral axis. So I've already established that. For axis asymmetric bending, so bending that is not completely symmetric, so you have an my and mc, but they're not necessarily of the same magnitude. Neutral axis may not be parallel to the y or z axis. Okay, so what that last point essentially means is that if you have asymmetric bending, your neutral axis is going to rotate about the centroid. So you're going to get your neutral axis happening at an angle in your cross section rather than parallel with your y or z axis. So that's essentially all that says. So how we find the neutral axis orientation, right, is if you remember from equation 12. So from equation 12, we know that the normal stresses have to equal 0. So this entire thing has to equal 0 first. The next thing, we're going to assume that there's no normal loads. So orientation of the neutral axis. Okay. Assume with equation 12, assuming no normal loads, okay, assuming no normal loads, we essentially get the following. So stress has to equal 0, or the normal stresses have to equal 0. Oh, by the way, I should go ahead and mention this. I'm going to call this right here, just to put it into a simple component, A, and this right here, including the negative, actually excluding the negative, sorry, we're not taking a negative in this. B right here. So yeah, essentially what I'm just using these substitute variables so I don't have to write the whole thing out over and over again. Okay, so it's A times Z minus B times Y. Okay, so basically do a algebraic or arithmetic here. You will get Y divided by Z is equal to A over B. Okay, simple enough. So how you would find this angle, assuming, well, not using small angle approximations, just using basic trigonometry, tangent, that orientation angle is equal to whatever y position, rise, run, whatever z position you have, and we have that equal to A and B. So in essence, you can find that orientation by just finding the following equation, where A and B are basically constants here. And that's basically how to find the orientation of the neutral axis. Why it's important to find the orientation of the neutral axis. That's another important issue to talk about, because we need to find where the maximum stress is, or then maximum normal stress is. Maximum normal stress for beams. Okay, so here, let's say we have some sort of, not really well drawn, but some sort of L cross section here, okay? So say we have something like that to deal with. And we're gonna say that the centroid is somewhere around here. And my y, just to be consistent, that's my y and that's my z-axis right there. Obviously x is coming towards us. And say we have the neutral axis about there, right? We found what this data is from the last, from this earlier. Okay, so now that we have the neutral axis, now what do we do? How do we find maximum stress? Now, you go back into our stress equation here. Sorry, if you go back to equation 12 here, essentially you choose a y and z location, right, to analyze your normal stresses, and you would multiply it by these in here, which are basically they're constants here, and you can exclude the normal stresses because the normal stresses are not dependent on z or y location. So you can just add this towards the end here, but you're really interested in which where the maximum bending normal stress is, or stress due to bending is. So it'd be the farthest location in the y and z direction with respect to the centroid. So you would have to analyze several points that you would assume is the farthest, but it would be one far for z and one far for y. You would essentially just need to target the farthest point in order to get the maximum stress. So there are times where you're going to have to target multiple different points, compare to one another, and see which ones, which normal stress is larger, and that's how you find the maximum normal stress. Now remember, one side has to be completely positive, the other side has to be completely negative. So if you have to look at the maximum negative or compressive stress, or if you find the compressive at one side and the other side has to be tensile stress, you'll have to look at the farthest point there. And if points are almost looking like they're equidistant from one another, you're going to have to compare between points to see which one's larger. I don't like how I had this thing here. I'm going to make that look a lot better. Okay. So a general set of notes that I need to write here. Okay, so I essentially wrote what I just said here when I share the notes, and you guys can just follow along with the thought process here. So yeah, that's essentially how you find the normal stresses in the beam, or the maximum normal stresses within the beam. So let's go ahead and do one example before we end beam theory here, so you have an idea of how to apply this in an actual problem statement. Okay, give me 1 second. I need my PowerPoint to load. Okay, so let's go ahead and start with an example problem. And for this example problem, we're going to look for the maximum deflection for a simple supported, simply supported, and we usually term this as simplify as SS, simply supported distributed load beam. Okay, so that is our example right here. Just going to go ahead and put example. So here's how we start. So here's our y. Here's our line. Oh, I do not draw this well at all. Give me 1 second. Okay, so it doesn't really look too clean, but you basically get the gist of it. Here is our beam. Let's assume there is, okay, let's assume there is a consistent loading, a uniform loading Wx here, okay? Simply supported, what simply supported means is that it's hinged on both ends. So it has a vertical and horizontal reaction here. Obviously, Z is going out of the page towards us, okay? So simply do a free body diagram with this, and you'll know what the reactions are. The vertical reactions are here and here are. So the vertical reaction here and here would simply be W times L over 2. Oh, by the way, the beam length is just arbitrary L. And then WL over 2, okay? So there's our problem set up right there. So to find the maximum deflection of this beam, the first thing we need to establish is, so let's go back and the steps I wrote over here. Let's go ahead and find the resultant force moments and shear moments, okay? Not resultant, but force and shear moments, okay? So with W here, W is, oh geez. W is equivalent to a normal distributed load in the y direction, okay? So W here is in the negative, so negative W, and remember one of the equations was, and I'm going to remove the subscript, so because we have a general 2D equation here, it's not necessary to put the subscript right now, unless we're dealing with a three-dimensional entity here. So I'm going to go ahead and remove the subscript for y. So equal to negative Wx, okay? Now this right here, the shear force, so V as in the shear force, if you carry out this integral, you get the following. The distributed load is a function of x multiplied by x plus some constant C1. How do you find C1? You use the boundary condition. So at x equals 0, okay, when this part goes away, what is the normal shear load? So the normal shear load is, we've already established right here, WL over 2 equals C1, okay? So in this equation, the consistent shear load within this problem is WL over 2 minus minus W. I should be a little consistent here. Minus X, okay? So there's our shear load equation. So now we need to find the moment. The moment would be found using one of the later governing or differential equations, where the moment is equal to the or differential moment with respect to x equal to shear load, which basically means if you just do the derivative of these, or of this, if you do the integral of this shear load equation we have right here, you essentially find, gonna go ahead and skip some steps, that, and apply the boundary conditions too, that the moment is equal to distributed load times L over 2 times X minus W X squared over 2, okay? So now we have our moment equation here. We're gonna go ahead and use equation 8. Equation 8, I believe, we have somewhere here. We're gonna go ahead and use equation 8 to find the deflection in the y direction. And for equation 8 right here, I'm going to imply 8 star. We're going to use equation 8 star because we're going to assume it's symmetric. So assuming symmetry here. Okay, so by assuming symmetry, we have, so I'm going to replace V because I don't want to get you guys confused with shear load V. The following, again, I'm going to remove subscripts because right now we are dealing with a 2D case, so having subscripts is not really necessary at this point. Okay, so from equation 8, 8 prime or 8 star. So I'm going to go ahead and just run through the integral. Again, apply your boundary conditions. The end goal of this integral will become something like this. So you guys can do the math yourselves at home. EI times, well, I guess I will show you the step before you apply the boundary condition, which is carrying out the integral. Whoops. Minus W for 24, okay, plus C3x plus constant 4. Okay, so these constants you're going to have to solve by applying the boundary conditions. So apply the following boundary conditions. So I'm just going to specify what the boundary conditions are. You guys will just do that yourselves at home. 0, when x equals 0, deflection equals 0. So C4 equal 0. Okay. At x equals the length L. Okay. So there's no deflection in the y direction, so deflection is still 0. Okay. So C3 has to become the following. C3 becomes 1 over Young's modulus divided by the inertia. Inertia about z, by the way, times distributed load cubed divided by 24 minus distributed load cubed divided by, now that I'm looking at this, I really should have simplified this. So this is simply WL cubed over 12, but guess you can do that later, derivation. So yeah, that is essentially your third coefficient that you need to solve. So apply that back in the deflection equation, and your overall deflection equation becomes as follows. That's whatever x location you so choose in the problem. 24 times the Young's modulus times the inertia, multiplied in brackets, the length cubed minus 2L x squared plus x cubed, right? And so now you have your deflection equation. Now you just analyze deflection at multiple different parts to see where the maximum deflection is. Now, obviously, the maximum deflection happens at the center. So you evaluate this at L over 2, you get the maximum deflection. So just something to bring up. Let's go ahead and look at our courses, Mechanics of Materials ebook here. So let's go to beam, shear moments. Oh, sorry, beam deflections. We're going to go ahead and look at integration of load, theory, sorry, we're going to go ahead and look at method of superposition, theory, Now we have load deflection equations right here. Now we actually have an appendix here that you can use instead of, so in our course catalog for mechanics and materials here, we can compare what we derived here with already derived beam equation appendix for a 2D case. So we have this sample right here, simply supported with a distributed load. And our result right here, our equation for beam deflection, is the same exact thing as what we derived, or what they have in the book here. And obviously the maximum deflection happens at the center, which yields this following equation. So this is very encouraging. This shows that our derivation is consistent with prior mechanical material methods. So yeah, we know that this is the correct equation, and we just simply use it to our advantage. So you can also apply that into rotation too, and rotation is simply the derivative of the deflection equation, and yeah, you will yield the both the rotation maximum. You can find both the maximum rotation and the maximum deflection of a simply supported beam, and we have this for multiple different configurations of beam analysis you would like to try out. And other than that, that is simply all I need to cover for beam analysis. Now, the only last thing I need to mention is the method of superposition. So what happens if you have an extremely complicated case where you have multiple different loads on one singular beam and you need to find deflection? Well, there's this thing called the method of superposition, which is you would simply, for example, you have a distributed couple on one end, you have a bending moment on the simply supported. What you would do is you would just split this into just a singular loading due to the coupling, and then singular loading due to the moment, and then you would add the deflections, simply add the deflections, and it will, at whatever x direction you so desire, and it will yield a close approximity result of what the deflection would be when both loads are considered. So that's really all there is for beam theory. And yeah, if you guys have any questions, just let me know.